In this video I will explain to you the concept of maximum power transfer and at the example of a solar cell, and we will connect in an experiment a certain range of resistors to this cell to find out the resistor which maximizes the power output of the cell. My name is Andreas from The Fearless Engineer, and here we go. Now, before we start with this experiment here, let's talk about this concept of maximum power transfer. Let me give you some background information first. In practice, you will note that there are no perfect voltage sources which deliver both constant power output and constant voltage across the terminals, which is independent of load resistance. This is going to vary in practice. Let's say you have a 9-volt battery and you connect it to a certain load resistance, then you will find that the voltage drop across the terminal is not as constant as you might have thought. It's going to vary, might be a slight variation, might be a larger variation, and it's going to be dependent of the load resistance, which is a property of the circuit which you connect the battery to. So this is going to change. The power source is going to vary its output. And if the size of the load resistor is chosen in a clever way, the source can operate at its maximum power. And this is the idea of this video. Enable you to choose the size of a load resistor in a clever manner that you can use to maximize power output, which is what we call maximum power transfer. This is the concept about which this video is mostly about. The last item here is that maximum power transfer is especially useful for sources which only generate a very small amount of electrical power. This might be a reception antenna, an antenna for receiving very weak signals. Such antennas need to make most efficient use of the electrical power from the signal which they receive. So such an antenna must be designed so that the power is maximized, and the same holds true for solar cells, which are used in a way that the connected load resistance is always chosen in a way that the power output of the cell is maximized, so we don't waste the precious solar energy the cell harvests at a given time. Let's also talk about the motivation behind this video. We want to talk about both the maximum power transfer concept, but also about solar cells, and we want to maximize the yield of a solar cell, the power output of a solar cell. So the resistance of the connected load should be selected in a clever way such that the output power is maximized in this maximum power transfer sense, which we talked about on the last slide. The approach consists of 4 steps. The first is to design the actual experimental circuit. Take a look at how we connect the various devices to each other. Secondly, we want to measure the current voltage characteristic for low light intensity. There's a light shining on the solar cell, and this has a low light setting. Then we do the same again, the voltage current characteristic for a higher light setting. And lastly, we're going to determine the maximum power for both light intensities. We're going to look if there is a peak in the power production of this solar cell here for a certain load resistance. Now this here is the actual experimental setup. You can see a light bulb on the left side, which is powered by this supply unit here. And by choosing 2 settings of voltage, you can increase or decrease the brightness of this light here, of this incandescent lamp. And in this way vary the amount of light which falls onto the solar cell. And connected to the solar cell is a resistor box which has a lot of switches on it, and you can flip the switches to very finely adjust the resistance value of this entire box here. So by flipping a few switches, we can very quickly change the resistance value of the load connected to the solar cell. We also are going to measure the voltage drop across the terminals of this resistor here. And also, because we want to find out the power consumption of this load resistor here, we are also going to measure the current flow through the resistor by using a second multimeter set to current measurements. That's the experimental setup we will look at in the practical part of this video here. Now the idea of this setup here is to find out which resistor maximizes the output of this small solar cell here. In the actual experiment, this light bulb here is used to shed light onto the solar cell, and we will choose two brightness settings for this light bulb here. One is set to 6 volts, which will produce a decent amount of light, but it will be called the low light setting. And in the second measurement series, we're going to lay 9 volts across the connector pins of the light bulb, producing more light, and this is going to be the high intensity setting. Okay, this solar cell here is connected in series to this multimeter here, which is measuring milliamps of current at this moment in time. And the ambient light surrounding the experiment here is currently enough to produce a current flow of 3.87 milliamps, roughly. It's fluctuating a little bit depending on where I put my hand in the setup here. If I cover the solar cell, you can see it go down. Now it's going up again. On the left, you can see another multimeter which is measuring the voltage drop across the connector pins of the solar cell. Currently, there's almost no voltage drop. It's at 0.015 volts. The reason why this is the case is that we did not connect any resistance value at all to the solar cell. This is the job of this blue box here. And all the switches which you can see here allow me to adjust the resistance value of my choice in a very finely grained manner. For example, if I wanted to set the resistance value to 122 ohms, I can simply flick the 100 switch, then the 20 switch, and then the 2 switch here, and now I have 122 ohms connected in series to the solar cell. And as you can see, the current has gone down to 2.8 milliamps only, and the voltage has gone up, the voltage drop to 0.35 something volts, which are measured across the terminals or the connector pins leading to this resistor here. Now let's set them back to 0, and now let's find the first setting, or let's adjust the light bulb to the first setting of ambient light, which is reached by laying 6 volts across the connector pins, which I have done now. And as you can see, the light bulb has increased its brightness. It's now shedding light onto the solar cell here, and the current flow has gone up to 31.1 milliamps, while the voltage drop is now at 0.119 volts. Now let's walk quickly through a measurement series where I increase the resistance value of the box from 0 to 100 ohms in 10 ohm increments. And I'm doing this quickly, and we're going to record all the values into a current voltage characteristic afterwards. So this is the first setting, low light 6 volts and 0 ohms, which is what you can read currently. Now 10 ohms, 20 ohms, 30 ohms, 40 ohms, 50 ohms, 60 ohms, 70 ohms, 80 ohms, 90 ohms, 100 ohms. And for the last setting, we're down to 5.13 milliamps, and the voltage drop is at 0.530 volts. Okay, now let's reset the box here and go to the second setting, which is 9 volts. As you can see, the brightness of the LED has now increased, and the current flow is now at 74 milliamps for the 0 ohm setting, and the voltage drop is at 0.282 volts. Now let's walk through the measurement series once more. 10 ohms, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, this is the last setting. Now we're going to look at the current voltage characteristic to compare the high intensity light setting to the low light setting. Now let's take a look at the results, at the resulting characteristics, which we could generate by using our measurements. On the left side, you can see the characteristic, the current voltage characteristic for the low light setting. You can see that with increasing voltage, the current first slowly, then quickly drops. So there's an inverse relationship between voltage and current. The higher the voltage, the lower the current. But for the first phase here, somewhere between 0.1 volts and 0.4 volts, the current flow remains roughly constant, which is why sometimes under certain parameters and circumstances, a solar cell is also referred to as a constant current source, because independent from the connected load, it still is able to provide a constant current flow. Even though between these 2 points here, this one and that one, there are no other load resistors which we connected to the load, but if we chose a resistance value somewhere between these two, it wouldn't have varied the current flow or the current flow generated by the solar cell. On the right side, for the high powers, for the high intensity light setting, the curve looks a little bit different. There's not so much this constant part, but we have this slight decrease in the beginning, somewhere between 0.2 volts and 0.4 volts. Then it gets quicker, and towards the end we have the majority of the points being very close, in close proximity to each other. And just as before, a higher voltage corresponds to an increase in voltage corresponds to a drop in the current flow. But as we want to talk about power, what we have to do now, we have to compute the actual power consumption or the power generation of the solar cell, or the power consumption at the load resistor, by using these pairs of current and voltage, which is what we'll do on the next slide. And on this slide we have power over resistance shown for both the low light case in the left diagram and the high intensity light case in the right diagram. And as you can see, there's in both cases a clear maximum, which is at around 20 ohms for the low light setting and at around 10 ohms for the high intensity setting. And after this setting has been reached, for higher resistance values, the power consumption significantly drops, which makes it a good idea for the respective light settings to use a 20 ohm load resistor and a 10 ohm load resistor. The problem is that the only thing differing between these two measurement curves is the amount of light falling onto the solar cell. Apart from that, everything else has remained identical. So the conclusion is, for solar cells, the power consumption varies with the light intensity which falls onto the solar cell, and also, this is an obvious fact, but also the load resistor which we need to connect to the solar cell in order to maximize the power output also varies with light intensity, which leads to the necessity in practice to track the resistance value for a solar cell, for, let's say, the solar cell on your roof. There's a circuit which looks at the amount of ambient light, which looks at the voltage drop of the solar cell, also its current flow, and which chooses the best fit in terms of a connected load resistor, which maximizes the power yield, the effectiveness of the solar cell for every ambient light level. So this power point, this point of maximum power, is tracked for the solar cell, which is why it's called maximum power point tracking in practice. This is what's done in a solar cell. And in this very simple experiment, you have seen why this is necessary. So let's look at the major takeaways from this video. First, we have seen that up to a voltage of approximately 450 millivolts, the current flow produced by the solar cell drops very slightly, which is why it's sometimes also called a constant current source. And at low light intensity, this really is almost linear up to this value. For high intensity settings, the behavior changes, and I wouldn't go as far as to call it a constant current source, at least this solar cell, for high levels of ambient light. And secondly, for higher voltage values, the current drops very quickly, as we have seen. The power diagram, if we apply the power law to this current voltage characteristic, shows a pronounced maximum, which is at approximately 20 ohms for this solar cell, which corresponds to the low light setting, and at approximately 10 ohms for the high intensity light setting. And this maximum power depends on the light intensity, as we have seen, and shifts to smaller load resistance values as the amount of ambient light increases, which is why in practice solar cells apply maximum power point tracking, as we have discussed on the previous slide. And last point here, this concept of maximum power transfer is useful when small powers are to be maximized, which is the case for a solar cell where we want to maximize the yield, and also for receiving antennas where we want to get the most out of a very weak signal we might receive with the antenna. That's all for now. If you have any questions related to this video, don't hesitate to drop me a comment down below in the comment section. Also, if you have any suggestions for future videos which you want me to make, please also leave a comment here. I wish you a nice day now, all the best, and see you next time here on The Fearless Engineer.